So this is not a fair comparison. They're not showing us the work. They've got this subjective beam efficiency. You don't know where the main lobe ends and the side lobe begins. They haven't defined the first null. These are electromagnetic simulations. These are not measured values.
Arrays are again at the bottom of the beam efficiency performance due to the many frequency-dependent side lobes collecting and transmitting the noise, hurting any and every WISP network out there. Dishes are somewhat better. Generally, the bigger the dish, the better the beam efficiency becomes, if the antenna is carefully designed and well manufactured on top of that.
Carefully designed and well manufactured. So how do they know if these are carefully designed and well manufactured? Because they don't have the designs to create the beam efficiency values. These aren't even manufactured antennas. These are simulated antennas. So this is totally disingenuous.
Now, with any antenna, though, the compromises accepted at the design stage unfortunately cannot be compensated by manufacturing quality, since the real-world results are at best approaching the results which we get from the simulation. What is interesting here, though, is the ultra horn. Its beam efficiency is 99%. Now let that sink in for a second. Over the whole bandwidth of operation in both polarizations, the beam efficiency of ultra horn is practically perfect.
Call me unimpressed, because to me, it seems like they went out and looked for some antenna parameter that they could use to toot their own horn. This is a cherry-picked antenna parameter. And then they cherry-picked how they calculate this. Of course, they're also going to cherry-pick what they consider the main lobe and the side lobes, because they haven't defined that. So this is just totally cherry-picked information here. This is not impressive.
Percent of the RF signal goes into side lobe. So if you ever wondered if ultra horn was worth the extra cash compared to a dish with similar gain, you have a very clear answer here. With 99% beam efficiency, it is the best performing antenna on the market in terms of noise suppression.
So a couple things there. In terms of gain, the ultra horn has 24 dBi of gain. The Ubiquiti light beam and a $69 integrated antenna has 23 dBi of gain. These are comparable antennas. Now it's possible that the ultra horn is going to outperform a light beam. The ultra horn is what? 10 times the cost? So is it worth the cost? It depends on the application. The light beam is obviously much better for most subscriber applications than the ultra horn. So the ultra horn is obviously not worth the extra money in terms of that application. You're not going to stick ultra horns on subscriber roof. But also, the cost determines the application. You're not going to compare similar gain antennas when you've got a 10x price differential. What you want to actually compare is similarly priced antennas. So what's a similarly priced antenna to this? Cyber antennas, this antenna is half the cost of the ultra horn. And this is going to outperform the ultra horn every time, in every setting. There's no way that the ultra horn would beat this antenna anywhere. But particularly in point-to-point applications, the ultra horn has a 10 or 15 degree beam width main lobe. That's looking like a main lobe that looks like this. It doesn't matter if that energy is contained in the main lobe or in the side lobes. What you want is the energy focused at a specific point in point-to-point application. You want as much of that energy focused at a single point. Noise resistance is not having all the energy in the main lobe and no energy in the side lobes. Noise resistance is having as much energy at the specific point and as least energy everywhere else. By moving some of the side lobes into the main lobe, that may help if the noise is co-located. But if the noise is coming from between the two links, then having that wider beam width is not going to help at all. In fact, you could be picking up more noise from between the 2 points. Keep that in mind too. So the comparison is not similar gain antennas. The comparison really is similar priced antennas. And for the price of an ultra horn, you can get a lot of high quality dish antennas, including deep dish antennas with excellent side lobe performance, as determined by industry standard antenna parameters, not nonsense antenna parameters like this.
Good thing is you can use ultra horn not only for point to point but also for multi-point coverage. With the option of tilting the antenna down, you can actually dynamically adjust the coverage. So it's really a very versatile tool, the best tool in terms of noise suppression.
Not the best tool in terms of noise suppression, but on using the ultra horn for point to point versus point to multipoint, you can also do that with a 23 dBi dish. You can also use a 23 dBi dish for point to multipoint with good effect, particularly a deep dish. So if you have a deep dish that's 23 dBi gain or 24 dBi gain, that's about a 1 foot dish or a 0.3 meter dish. Then you can also use it for point to multipoint application. You just need to keep the stations within the beam width.
Beam efficiency tells you everything about side lobe performance. The higher the beam efficiency is, the better an antenna performs, period. So forget about frontal big ratio, side lobe level, or ETSI masks and really focus on...
Why would you forget about those other antenna parameters? Even if you fully swallowed everything that RF Elements is putting out there, why would you dismiss everything else? Why would you forget about everything else? Are they trying to educate here? Or are they just trying to market their products as the best? Obviously, they're just trying to market their products as the best. So RF Elements does not deserve credit for enlightening WISPs, for educating WISPs, for helping WISPs better understand how to deal with noise. They don't deserve that credit. They stumbled on horn antennas. Horn antennas perform well in noisy environments because of their narrow beam widths. RF Elements never understood that, so they went looking for reasons why their antennas performed well in noise. They came up with side lobes, but mostly what helps with co-located noise is GPS sync. And then they created this antenna parameter, this beam efficiency antenna parameter, as a way of explaining it, but they never understood any of it.
Beam efficiency of an antenna when dealing with noise. Not only it's the most complete measure of side lobes, but it's also extremely robust measure of side lobes because
neither complete nor robust. So complete would be taking into account the entire frequency range that the antenna is operating in. It would be giving you the worst case value, not averaging everything together. And to be robust, it really needs to be useful, right? So you have to have a way to apply this knowledge. It doesn't do anything for you. The only thing it possibly could help you with is product comparison. But you have to take RF Elements' word for it. And they're not a trustworthy source on this. They've proven that many times over.
As well, ask them if it's averaged over the whole useful bandwidth and both polarizations to make sure.
RF Elements, how about you show us your work? How about you show us how you calculated these beam efficiency values? How about you show us the details, not just make blanket statements? How about you show us measuring the beam efficiency of your antennas and then comparing that with your modeled values? That's science. So how about you do some of the work rather than put it on us to ask our antenna vendors to conform to your nonsense antenna parameter?
The comparison is fair, since it rarely happens that a wireless link is situated in a completely isolated place. The interference is present practically everywhere. The noisier the environment, the more important beam efficiency of an antenna you use becomes, because the higher the beam efficiency, the better noise isolation. And recently, you can also hear claims from other antenna manufacturers saying, for example, this sector patch array antenna works like horn in terms of avoiding the noise. Similar statements. And to these claims, I would just ask a single question. What is the average beam efficiency of that antenna? Now, if the beam efficiency of that antenna is of similar values, then I would stay quiet and say, yes, I agree. But otherwise, if the beam efficiency is anything below 90%, you can be sure that they're really not the same, and the claims of the manufacturers are probably more of a marketing fluff than anything else.
So apparently, some antenna manufacturer, I have a guess, but some antenna manufacturer was saying their antennas perform like horn antennas. Probably what was happening there is an antenna manufacturer was making sector antennas that have narrow beam widths. With those narrow beam widths, you can have a sector antenna that performs similar to a horn antenna so far as a horn antenna has a narrow beam width. Obviously, RF Elements doesn't want customers to understand it's the narrow beam width of horn antennas that make them perform well in noise, not the no side lobes. And so it appears that they created this beam efficiency as a way of debunking their competitors' claim their sectors were performing similar to horn antennas. That seems to be actually what's going on here.
And in the following section, I will tell you about the practical implications and consequences. So, using an antenna with high beam efficiency, we can sum up the effect of high beam efficiency antennas into one statement: higher throughput. In a sector with no other links in the area, you don't mind the side lobes, but as the number of sectors grows, their side lobes cause the noise floor to rise. And higher noise floor equals lower SNR the radios are working with, and eventually lower throughput.
So what causes the noise to rise is these wide beam widths. So you can see they're actually contradicting themselves right here, because you've got this sector. This is all part of the main beam. This is not side lobe. This is part of the main lobe. And they're calling that noise. You could have 100% beam efficiency, and you can have a main lobe shaped like this that's picking up all of this noise.
The beam efficiency of patch array sectors is on the order of 60%, as we saw. The remaining 40% of the energy is in the side lobes that collect and transmit interference to other links within yours, but also competitors' networks, obviously. So low beam efficiency equals lower throughput, consequentially more unsatisfied customers, constant issues with your network, and that keeps you unnecessarily busy. Low beam efficiency of dish antennas works in a very similar way. It's really the same, but not different, really. The side lobes collect the noise from its surroundings.
So just notice there's a single point here, and you need to